Hi, my name is Griffin Rice, and this is my report for Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to observe the distance dependence of the magnetic field of a small bar magnet and measure the magnitude and direction of the magnetic field on axis and off axis using the Biot-Savart law. We also want to compare the measured magnetic fields to a computational model also representing the magnetic fields, and we will find that the magnetic field is stronger when it is measured closer to the source. As for the initial conditions in this lab, just have the magnetic constant, which is equal to mu0 over 4 pi, which is equal to 1 times 10 to the negative 7th. System and surroundings. System, in this case, is the magnetometer, and the only thing we have in the surroundings is the bar magnet that is creating the magnetic field that we're measuring. Some of the fundamental principles and concepts in this lab, the Biot-Savart law for magnetic dipoles, the formula for distance dependence of the bar magnet, which is the magnitude of the bar magnet's magnetic field equal to kr to the n. And then we're also trying to find the magnetic dipole moment of the bar magnet, mu, and we will not be using this specific formula, but rather deriving mu from the Biot-Savart law formula and the distance dependence formula. As for the procedure for this experiment, we first calibrated the magnetometer to align with the Earth's magnetic north pole, then tested the magnet's magnetic field by placing the phone at various points, both parallel and perpendicular to the magnet's dipole axis, then recorded the distance between the phone and the magnet, as well as the magnetic field value from the app at each of these points. We then used these data points to plot a linear regression model, seen below, and to find n, k, and mu. And the line we got, the regression line we got was y equals negative 2.5339 x minus 14.577, and then r in this case is just the slope of this line. K is equal to 4.6697 e to the negative 7th, and then therefore from using these values we found mu to be equal to 2.33485, and then through our observations we found that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And here are some of the observations from the experiment recorded in the Excel spreadsheet. We have the distances of magnetic fields for both on the points both on and off axis, and then the plot of the linear regression line. And then here's some of the code used to create the computational model. We first created the bar magnet, used the magnitude of the mu value we got from the experiment, create a function calculating the magnetic field of the magnetic dipole representing the bar magnet, create the observation locations both on and off axis, created the parallel arrows, created the perpendicular arrows, and then created the arrow for the magnetic field 45 degrees off axis. And then here's the model itself. The cylinder in the middle is the bar magnet. Orange arrows represent the on-axis magnetic fields. Cyan arrows represent the perpendicular to the axis magnetic fields. And then the magenta arrow is the magnetic field 45 degrees off the axis. Some sources of error present in this experiment. Slight errors and inconsistencies in the magnetometer readings, interference from other magnetic fields in the room. For example, like light bulbs, other electrical equipment creating their own magnetic fields, inconsistency in the phone placement, and error in measuring distance between magnetometer and bar magnet. To answer the first what-if question, if the experiment had not been oriented to compensate for magnetic north, Earth's magnetic field would have skewed the readings from the magnetometer and caused the x components of all the magnetic fields to be off by the same amount. And to answer the other what-if question, if the experiment was performed again with two bar magnets stuck together on the ends, we would expect similar results since they would still act like a bar magnet, but the magnitudes of the magnetic fields would likely be higher since the combined magnets would create a larger dipole moment.